All right, let's talk about some calculus. Okay. All right, so each strand of maths kind of has a different idea behind it. For instance, let's think about 3 other major strands of maths which you have already come across. What would you say was the idea behind geometry? What does it deal with in general?
Shapes.
Yeah. So like shapes and space. Spaces in shapes, around shapes. All that. That's geometry pretty much. Algebra.
Numbers and equations.
Yeah. Rigel?
Finding X.
Finding X. It's always finding X, isn't it?
Yeah.
It's about the relationship. The way X and Y kind of unknowns interact. So like when you're forming formulas from sequences and stuff like that, you're looking at the relationship, inputs, outputs, that kind of stuff. Probability then is
Probability.
Probability is probability. It sure is probability. Is there another word?
Chance.
Chance, yeah, chance, or perhaps uncertainty. I don't know if I spelled that right, but I get the idea. All right, and that comes now calculus. You know what the
Curves, I don't know. Like slopes and stuff like that to do with curves.
Slopes and stuff like that to do with curves.
It's like area under a curve, gradient at a certain point.
That sounds like geometry.
A complex curve. I don't know.
It's about change. Yeah. You're giving me stuff that's in context. Yeah. So it's the maths of all things that change, that are not a constant relationship. So in algebra, they're kind of constant relationships. Calculus is stuff that change, things that maybe accelerate, for example. So it's the maths of all things that changes. The proper name for calculus is actually called infinitesimal calculus, but we don't use that. We just shorten it down for calculus. Calculus, of course, you always see in maths, such a calculator. Where else do we see it? No, I couldn't think of calculator now that I said it. But calc or calculus, I can't remember which one. It stands for small pebble, and it's the pebbles that were used on an abacus. And calc is also related to chalk, so it's all intertwined. Ancient Rome was the first place that they used pebbles as units. I think it could have been Greece. Don't know. One of the two anyway, but it's Latin. Calculus is Latin, so I think it's wrong. All right. So what we are looking at, what the Americans would call AP calculus, advanced placement calculus, and we're also going to do pre-calc. And you know, the Americans might take 2 years to do that. We're not. And they would just focus on it. So we're just going to include it amongst probability, algebra, and geometry. We're going to do them all in 2 years because we're great. All right. Does anyone know who came up with calculus first? Come up with this idea?
Newton.
Newton and? What was that, Dustin?
I think it's Leibniz, the German guy.
Leibniz, yeah, the two of them. They fought over it. There is I think the common, don't quote me on this, you can research this if you want, I'm doing this off memory. The common idea is that they both discovered it at the same kind of time, and it's still up for the debate who discovered it first, I suppose, but that's just, yeah, I think it may have been Newton, but we won't worry about that too much. Anyway, those two guys fought over it, and you see the Leibniz notation that came up a little bit in the chapter. I think they discussed that, and we'll look at that in a minute. Okay, so I just wanted to talk about Newton. Let's go with Newton, because he, of course, of the apple fame. If we just create a graph here of gravity and its effect on that apple, I think this is perhaps where Newton came up with the idea of calculus. If I were to draw the graph of force versus the distance something is away from the ground, I think if it's pretty close to the ground, the force of this is gravity on that apple falling on top of Newton. There he is under the tree. Look at that. There's an apple here. So the closer the apple is to the ground, the more gravity works in it. But if the apple is quite far away, the less gravity would work. So it's kind of like a graph like this, I think, something like that. Okay. So what he thought about was how did gravity change over distance, and what he noticed was that it's different everywhere we look. There's not a constant rate of it's not a constant slope here. It's different everywhere you look. So you could start to form straight lines here at a certain point. But he noticed anyway that there is not a constant change, it's more a changing change. Okay, at some places, this place is more steep than this place, which is more steep than this place, and is more steep than that place. So the steepness is constantly changing. So if you compare that to a straight line is easy to find, of course. We know that we can always find the gradient of a straight line. We can always find it's changing. Its changes rise, of course, over run. But that won't be able to be used here, he found. So he wanted to find, of course, the slope at a particular point. And what would that line be called then? If it was just at a particular point, and I'm sure you came across it.
Tangent.
Yeah, at a particular point, that would be a tangent. But in order to find a tangent, you of course need 2 points to compare, to get the gradient of 2 points in order to find the slope of that tangent. What 2 points do you use? Well, let's take you to a circle before we... Okay, so let's look at a tangent to a circle first of all. All right, let's draw some secant lines. Do you know what a secant line is?
Is it when it passes the circle, but it doesn't intersect the center?
Yeah, so that'd be a secant line. I'm going to draw secant lines that are parallel. So secant lines then would have chords inside them. And so a chord would be that distance between there and there. All right, so as this secant line is parallel to this tangent, as the secant line gets closer and closer, the chord gets smaller and smaller. Oh, hi, Mr. Henson.
Hi, Mr. Collins. We're back with you. Benai's back with you for the moment, and we'll catch you up later.
Okay.
All right. Cheers.
Cool. Okay. So as that, but we haven't really done very much. We're just talking about the history of calculus and how it came about, how did Newton come up with calculus. Anyway, he was looking to form this tangent line using chords, and he noticed that as he got closer and closer to the tangent line, the chord line got smaller and smaller until actually at the point of tangent, it's approaching the length of 0, but it can't get to 0 because then it wouldn't be a chord anymore. Okay, and he used that same theory behind the classic example, which brings you into how you find the gradient in general, which we'll look at right now that Badai is back. So that was perhaps slightly stally. All right, so we're looking to get that and apply it to a curve. Okay. Of course, the circle is full of curves, but we're looking to do that same principle. All right, so this is some function, y is equal to fx, some function. I'm constantly looking at the rate of change of this, and it's the same as my initial example. It's constantly changing. For instance, it's steeper here than it is here. And it's kind of in the middle of those two steepnesses there. All right. So in order to find the slope at any 2 points, you can, slope of a line at any 2 points, you can just get 2 points perhaps. So if we call this first point x, and you probably saw this in the example, if we call the distance between the 2 points h, this next point up here would be x plus h. So the distance between the 2 points is h. So we're talking about getting the slope of this line here. If I get the slope of that line, it's pretty close. It's pretty close to the general slope between here and here. It's not exact. Okay? All right. So that's the x's. Because I'm trying to find the triangle here. I'm trying to get the rise over the run, am I? I'm just trying to find this. All I'm trying to find is the slope of the line between these 2 points, which I don't know, but I've called x and x plus h. H is just the distance between the two. I'm trying to set up the slope of the line I've drawn, which technically is another secant line because it goes through the curve either side. Okay, and it's the rise over the run. Now I'm just looking at the run here. The run is from, well, we know it's h, but you can write it as, using your y2 minus y1, x2 minus x1 formula, can't you? X plus h is that second point of x, and the first point of x is just x. This is get you h anyway. That's going to be the run, the distance. That's just h. Okay. Cool. So just looking at this slope, but I need, of course, the rise. How much does it go up? So I need to compare it to the y-axis as well. How much does it increase? Now, if I put x into my function, I don't know what it is. It's just f of x. X going in is still just the function with x in it. So at that point, I could call it y, but for the purpose of this, I'm just going to call it the function with x in it. When I sub in x, I'll get the corresponding function with x subbed in. The same thing would happen when I sub in x plus h. I would get a corresponding x plus h here, wouldn't I? The function with x plus h put in it. Now, what's the difference between these two with y2, which is my second y point, minus y1 using my slope formula? So f of x plus h minus f of x. Take one away from the other, and that will form my slope formula. Remember, slope formula y2 minus y1. The second y point, take away the first y point. x2 minus x1. Now, once again, what are we trying to do here? We are trying to get the slope of this line. The slope of this line. It's a secant line. It touches the function at 2 points. And we're trying to get a general formula for the slope of that line. We don't know what the points are yet. Okay. So I simplify the bottom. X plus h, take away x is just h, which we kind of knew anyway. Can't really simplify the top because I don't have enough information to simplify at the moment. Okay. Now, this is the slope of that secant line. But of course, that's not a good representation of the slope of the curve at any particular point. Remember, the curve is, I'll highlight in yellow here. The curve actually doesn't match that at any point. So would perhaps you agree, and if you did your work on this in chapter 16, you probably saw, would you agree that if I make the distance between the 2 points closer and closer, I would get a more accurate estimation of exactly what the slope would be? And if I made it as close as possible, this h was a minuscule distance. For all purposes, that line, so if we just had a visual representation of that curve, if the points are quite far apart, like that doesn't match. So that's far apart h's. That doesn't really match the curve yet. If I drew the same curve, try to draw it, oh, that's terrible. But if I make them smaller, okay, that's getting pretty close, but there's still a gap here. So if I draw a curve and I make the distance between the 2 points so tiny you can't even see it, it's approaching a tangent, isn't it? The same way our chords in the circle earlier on approached the tangent. So if I make these distances between this h distance, if I say, so h is the distance between these two, h is the distance between, and h is in there. I did draw 2 points, but they're so close that you can't even see it. If I make that h tiny, I can find the instantaneous slope at any point, once I know the x point to put in. If I make that h tiny. Now, how do I say that mathematically? If I want to get h to be super small.
Limit.
Limit, exactly, yeah. Okay, so I might be going over stuff you already did. So if I want to find the slope of the tangent, I need to find the limit as h approaches 0. H can't be 0. Why can't it be 0?
Because then it's the same point.
Yes, the same point. You're not getting the distance between 2 points anymore. You're not getting the slope between 2 points. You're kind of ignoring it. And you'd be dividing by 0, which would be, of course, undefined. So for both those reasons. Now you saw, so if I do the slope of the, between the two, of the secant, or tangent now in this case, because I'm bringing them so close together, you saw this in your, hopefully in the, oh, minus, in the notes. And of course, this is the first principles of calculus. It's the first bit of calculus. I can find how steep this graph is at any point based off its finding its tangent, the slope of its tangent at any point. Now, this would be called, of course, well, maybe not of course, it's called the gradient function, then. It will give you the function of the gradients. It is also could be called the change in y. So as y changes, y2 minus y1 here on top, remember from our slope, as y changes over the change in x. So the change in x was just h, but we found it out here. X plus h, take away x, that's the change in x. How much has it changed? Now, that's quite a long way of writing it. And another word for change, perhaps anyone who does physics would know delta. So you could use delta y over delta x, the change in y over the change in x. I don't know, did you come across that in physics?
Yep.
Yeah.
And then do they just say dy dx?
Yeah. And then d for delta, dy dx. We don't use delta because it looks a bit like a triangle. I don't know if that's the reason we don't use delta. We just use dy dx, which is also called the derivative because it's derived from because it's derived from another function. It's called the derivative. Another way of writing that is kind of a f dash x, of course. If the function is fx, you would write the derivative or the gradient function as f dash x. So there's a couple of ways, and I'm sure you came across this. So if the function is written fx, you usually would write the derivative function as f dash x, or if it's written y, then it equals the derivative of y would be dy dx, the change in y over the change in x. And later on, we'll be looking at d2y dx squared, or the second derivative, which is the change of the change. What's the rate of change of the change? Also known as acceleration. How much the change is changing. Okay. But hopefully you get that concept, and hopefully this is the second time you're seeing this at least. That the whole basis is that you're finding the gradient of the tangent. And it's the tangent because this h distance is so small, it's minuscule, that we can say for all intents and purposes, the limit that it is the gradient at that point. Even though it's kind of not, but it is. Okay, so how do we apply first principles? I'm sure you've also done this, but let's just go through it to make sure we understand rather than just know. Okay, so we're going to apply that first principles. So in my previous example, I had no function. I just drew a sketch. But now we're going to look at applying it to a function and talking about what we've achieved. Okay, so I'm going to look at a basic function. I'm going to look at x squared. So x squared is this function here, something like that, isn't it? So that's my function. I'm going to call it fx is equal to x squared, or y is equal to x squared. All right, I'm going to apply my first principles here. So my first principles tells me that if I want to find the slope of any point on there, I'm going to have to use the slope of the tangent at that point. So I could go back and use the same definition of having 2 points further away, but I'm going to make that h really small. So I'm going to make those 2 points pretty much close together, so they're pretty much on the point. So how do I do that? Well, I once again look at the slope of the tangent. So this, when I do this, of course, this is no longer the function. It is the gradient function I'm trying to find. And to do that, I need to do f of x plus h minus f of x, so the change in y over the change in x, which we know is h from before. I'm going to find the limit as h gets to 0, as the distance between the 2 points gets to 0. And that slope will be the slope, the gradient function. It will be the slope of all points. Okay, so this time I actually have a function. I have x squared. So I need to find the function with x plus h put in it. So that's going to be x plus h squared. Take away the function with x put in it. Well, that's already there. Minus x squared. And that's all going to be divided by h. I'm going to eventually find the limit of that as h approaches 0. I'm sure you probably did this exact example. Okay, so this is squaring out, so hopefully we're able to do that. If you want me to slow down and do that again, I will. I still haven't evaluated as h approaches 0. I'm just going to tidy it up. Now, what should always happen here is that the original function kind of disappears. X squared take away x squared. That original function goes away, and only the stuff with h in it is applicable. Okay. So all I've done, y2 take away y1 over the change in x, which was h, and I'm making h tiny. Now is my time to start to make h tiny. Now if I make h approach 0 here, so approaching 0 makes h infinitesimal calculus. If I make h 0 here, I have a problem because it'll be dividing by 0. So if I do some factorizing, I'm sure you also did this. So I'm still not going to, I'm going to keep writing my limit as h approaches 0. I'm going to factor out the h here on top. I'm going to get 2x plus h, I think, and h in the bottom. Now that goes into that once. So I'm left with the limit as h approaches 0. So h has been factored out a little bit here of 2x plus h over 1, if you want. And now I can say, well, as h approaches 0, h is, you can pretty much say it's 0. Because it's going to be so small, it's going to have no effect. So what is the limit of this function as h approaches 0? Well, that h tends towards 0. So you could write an extra line, 2x plus 0, and then 2x. So f dash x is 2x. So I've evaluated the limit, so I don't need to write it anymore. And I had f dash x. So what is this?
The gradient function.
Thank you. It's the gradient function. Right. All right, I'm going to draw that gradient function now. So according to this, the gradient function, it goes through 0, 0, because it's got no y-intercept here at the end. And it's for every 1 it goes over, it goes up 2. So it's something like that. For every 1 it goes. Okay, so it's like that. Here's my photocopying card. There we go. So that's the gradient function. Pretty sketchy sketch, but that's it. What's that telling us?
It gives you the gradient at whatever x value for your parabola.
How do these two relate? This is my original function, fx is equal to x squared. How does it, yeah, it gives me a slope apparently, but does it make sense?
If you match the x point on the quadratic, for example, when x equals 3, that will be the slope of that given point using the gradient function.
So when x equals 3, we get 6 as the slope.
Yeah.
Okay. Yeah. But does it make sense that it's positive after this line is in the going to give positive y values after 0, and before 0 it gives negative y values?
Yeah, because the parabola, the tangents at the before x equals 0 on the parabola are going to be negative.
Yeah. So if we look at the parabola itself, all the slopes, if we drew tangents along this negative side, so if I drew in a tangent here, the tangent of that slope is negative. And if I drew in a tangent over on this side, the tangent of that slope is positive. In fact, all the tangents on this side are going to be going downhill if you drew in a tangent. So they're all negative slopes. All of them are negative slopes, so we can put them all in as negative. And on the other side, they're all positive slopes, aren't they? They're all going to go uphill. And in fact, they're all going to be increasing, aren't they? The further away from 0 we go on this graph, the steeper the slope would be, or wouldn't it, of the tangent? The further we go this way, that slope will get tighter and tighter. It will turn more. It will start go almost vertically eventually. It'll never be vertical, but it will get steeper and steeper. And that's what this is saying as well. The further we go here to x, you're going to get a larger value of y. In other words, the slope is going to increase and increase and increase. So if we put in 10, our slope is going to be 20. So for every 1 box this goes over, it goes up 20. So it's shooting up. But if we put in 100 and we go way down here, we're going to get 200. The slope is going to be 200. So for every 1 box it goes over at that point, it shoots up 200 on the y-axis. And you can see that's getting steeper and steeper. Now, of course, when I draw it, I'm not drawing it very well. But you have to notice that it is getting steeper and steeper, but it's still changing. It never reaches fully vertical. And you can see that here matches here. This point, does anyone know what that point is called? Where
Vertex, origin.
It's called a vertex in a quadratic. What's it called when we're talking about, so well, not obviously, the gradient at this point is 0, isn't it?
Yeah.
we could test that using the gradient function. Put 0 in, and you get 2 times 0, which is 0. So the gradient is 0. So it's kind of the tangent is flat at that point. What's that point called in calculus? Did anyone come across it? Begins with S. It's called a stationary point.
Oh, yeah.
Stationary point. Now, in this particular case, it's also a turning point because the graph turns at this point, isn't it? A stationary point is when the slope is 0. So you get this flat bit. It's a flat tangent at that point. So it's a stationary point. This one is also a turning point. So the slopes have changed from negative, hits this 0 point, and then goes to positive. Does that mean all stationary points are turning points?
No.
Give me an example of a stationary point that's not a turning point.
Sir, couldn't the quadratic also be just
When the quadratic is translated to the left or right.
So like x squared minus 3. That would still, that point there, wherever that point is, or up or down, so whatever quadratic you draw, that you'll get a stationary point. You'll get a point where when you sub something in, the slope is 0. Now, it mightn't be 0. It mightn't be when you sub in 0. It might be when you sub in 5. But you'll get 0 out. You get a 0 slope. Okay? The question I'm asking is, based on the shape of these graphs, that's a stationary point where the slope is 0. So every quadratic graph will have one of those. Won't it? No matter where it is. But does that mean all stationary points are turning points of all functions?
Sir, what about an exponential graph?
Justin?
Yeah, I said, what about an exponential graph? It doesn't have a turning point.
Does it have a stationary point though? So next, that's a good point. So exponential graph, going on and on and on. I'm not sure that has a point where the slope would ever be 0. I think it would always have some sort of slope, wouldn't it? But a good idea. There is a type of graph. Anyone think of it?
one with a turning point, sir?
One with a stationary point, but no turning point. So a turning point would suggest that it changes the slopes of the gradient.
Oh, isn't it an asymptote?
An asymptote? No.
It has you said a turning point?
Okay, so let's discuss what a stationary point is. Now that I've gone through it, Justin, tell me what you would think a stationary point means.
That's when the gradient is 0.
Yes, so the gradient of what?
The gradient of the graph line.
The gradient of the graphs, the curve here?
Yep.
Okay. Yeah, so the gradient of the tangent at that point is 0, yeah. Okay. Then a turning point is when that stationary point makes a switch from negative slopes to positive slopes of the tangents, like that. Now I'll give you an answer here. Think of the normal x cubed graph. That's the normal x cubed graph. Now at this point here, there is a stationary point, but it is not a turning point because that gives positive slopes, that'll give positive slopes, positive slopes. So it hasn't actually turned back, has it? So what do you think the graph, now this is perhaps conceptual at the moment, what do you think the graph of the slopes would look like here?
Would it be like an absolute value?
Not quite. Could be an absolute value, but I don't think it'd be as sharp as that. It's curving. So the slopes would be slowly decreasing towards 0 and then slowly increasing before shooting off. Think about that. The y values of the slopes would be slowly.
Oh, it's a quadratic.
It's a quadratic. Boom.
Oh, is that why you have to do multiple, I guess, gradient, whatever? So you eventually get down to a line?
No, you don't have to get to a line. No.
Oh, no.
What the gradient function will give you is the gradient at a point. Now, in this case, those points, so those gradients, form a quadratic, but you're still getting the equation of a tangent at a point. But when you put all the gradients together, they form a different function. It's a gradient function, but it only gives out the gradients. You still are talking about tangents. No matter what the curve is, we're still talking about tangents. So what do these pluses mean? That means that's the tangent at that particular point is positive. The tangent at this point is 0. The tangent up here is positive again. So what I'm graphing is no longer, it's okay that it's a quadratic. It's the slopes put together and it forms a quadratic, which is kind of cool. And if you want to get the second derivative, yes, as you said, you would get a line. But think about it. If we have a quartic function, the first derivative is going to give us a cubic graph. Notice the way we had a squared function here, x squared, and what we got out was a line. When we get an x cubed function, so this one, when I look at the slopes of an x cubed function, I get out a quadratic.
Oh, so like in terms of physics, so a quadratic saying, I don't know, dealing with velocity and time, then your acceleration, since you have to do the dy dx twice, would just be like a horizontal line, so it'd be constant. But then
if you get out on second derivative a straight line, the acceleration is constant, yes. But you can, of course, get out an acceleration that is not constant, which is obviously more real life applicable. You can get out an acceleration that is in itself a cubic graph. Because the acceleration could be going up and down, and people could be, stopping and starting and all that. So yes, often what you see when we deal with these they're called kinematics problems in maths. I don't know what they're called in physics, but the acceleration is a constant change. It'll be constantly negative or constantly positive. So you're either decelerating or accelerating. And that constant line would mean, because it's quite difficult to deal with accelerations that constantly change. But yeah. So how you go back through these, you can be given the acceleration, let's say, of something, and it is a cubic graph. And you can go backwards and find what the original graph was. Does anyone know what that's called?
Wait, sir, can you repeat that?
Okay. So this is derivation, where we take a graph and we look at its slopes along the graph. Derivation from the original function to get a derivation of the function that shows the gradients along it. What's it called when we're given the gradient function and we want to find out what its parent function would be? Let's say underive. What's it called when we underive something? Does anyone know what that's called? Going from here back to here is called integration.
Oh.
And that's with that fancy symbol. You might have seen this. Okay, so often it's like 2x dx between 2 and 0, and you can see stuff like that. The 2 and 0 is finding an area, but we'll get to that later on. But this integration brings you from the derivation back to the previous. And you can integrate this, because this, of course, albeit the parent function of what we're dealing with, if we integrate this, we would go back and find a cubic function, which of course this would be the set of slopes of a cubic function. Does anyone know what the cubic function would be? It wouldn't be x cubed.
It would be 2x cubed.
I think 2x cubed? No, it wouldn't be 2x cubed.
Well, like x cubed would be 3x squared, right?
Yeah, x cubed would be 3x squared, yes, derived, yeah, by rule, yeah.
So 1/2 or something.
Think about it, so it's over, perhaps over 3.
Yeah.
Because if I do that by rule, I multiply down by 3, and I get 3x squared all over 3, and the 3's are cancelled. So it's actually, this would be the parent function for this. And then, of course, that would also show the slopes of a quartic, and you can do that too, and so on and so forth. So there's interrelations between derivatives and integration. We'll get to integration much later on, but this just shows that it's all just linked. And they're all, of course, they're all not theoretical. What you're dealing with questions that have no applications at the moment. You're just dealing with find from first principles the gradient function, or was it, how would they write it? Find from first principles the gradient function of fx when fx is something, x squared minus 3x. You're asked to find that. But of course, what you're doing is you're finding a general gradient function for that piece of algebra, I suppose, at the moment, or that function at the moment. And later on, that function will have a real thing, a real basis to it. It will be a car accelerating or decelerating. It'll be a sphere expanding or filling with water or deflating or something. It will have some purpose. Now, at the moment, you're just doing the theory. So let's look at another theory question. So later on, we can develop the purpose. But we're always try and understand calculus as you do. Do not learn things off by heart here. Please don't start to learn first principles off by heart. So let's look at one. I'm just going to pick one randomly from the book, from first principles. Let's do another one that's a quadratic, or let's do a cubic. Okay, so I've taken one from page 428 here. I haven't done this already, so let's see how it goes. All right. And they're saying to do this from first principles, yada, yada, yada. Find dy dx from first principles. Okay. First of all, when I put, so let's say that's fx. I prefer fx, but it doesn't really matter. When I put something into that, so let's say I put 1 into that, what am I getting? So you can tell me literally what I'm getting if you want to just work out that number.
2.
Or
Yeah,
getting
2.
2.
Sorry.
So it'd be 1 cubed, 1, take away 2 times 2, or 2 times 1, sorry. Isn't that 2? Isn't it 1 take away 2 plus 3? It'd be 2. Yeah. Confused myself there. What is that? What is that? What have I formed?
The value of y when x equals 1 of the function.
Okay, so I found, yes, the value of y when x equals 1. So I found a point. I can plot that, can't I? 1, 2. I know that's on that graph, whatever the graph looks like. Yeah? That's 1 point. And if I put in any value here, I'll get a y value out, and that will also be on the graph, won't it? If I get enough of them together, I would form that graph. I could just join the dots, if it will. Of course, that's a long way of doing it. Now, what do I get when I put 1 into the f dash function?
The slope at that point?
Yeah, I'll get a slope of the tangent at that point. How did I get it? Well, I got it from first principles, which I'll do in a second, by making the h distance between 2 points So I start off with thinking about it, once again, a secant line, or just a line between 2 points, and I make that h so tiny that it's a tangent. And I get a slope at a point. So I don't know what that is yet. Let's say it is, well, I could probably figure it out. 3 points. I think it's 1. So I get 1 out. Let's say I get 1. That is 1 point. But the same as if I sub in multiple values here. If I sub in multiple values here, once again, I will get a graph. What's that graph going to look like?
The gradient graph, you mean, sir?
Yeah, what's the gradient graph? What's the prediction of what it'll look like?
It'll look like some quadratic.
Yeah, you reckon it's going to look like a quadratic. Well,
Yeah, because it's
think
1
about
degree lower, right?
it's 1 degree. Yeah, so that's a cube. So if this is a normal cubic, I'm just going to is this going to be option 1, or is it going to be option 2, just by looking at the function?
2.
2, so it starts low and finishes high. Why do we know that?
Because it's not negative at the beginning.
Yeah, it's a positive x cubed, so positive x cubed is going to take over at either end. Yeah, so it's not 1, it's 2. So in general, this graph looks like that. Okay, and I don't think there's one of those flat turns there. Sorry, like the x cubed thing. I don't think so. It's possible, but I don't think so. Just because of the nature of the translation. Anyway, so let's talk about the slopes of this. The slopes of the tangents along this. What's the slope of tangent just here? Is it positive or negative? Just talking about.
Positive.
Positive, positive, positive. Stationary point.
0.
Turning point here. Stationary point, turning point. Negative, 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 negative. Stationary point, turning point. Yeah. Positive, 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 positive. So this is 2 stationary points. Okay. And as positives, then negative slopes just between this. Now, how does that relate to our graph of the gradients? Also known as the gradient function. Also known as the derivative function. How does that look? Well, let's think about it. At 2 points, it's at 0.
Oh, yeah. Those are its roots.
Between those 2 points, it goes below 0. And after that, it shoots off positive and negative. So they're all below 0. All the gradients are below 0, minuses. So this y-axis is not, of course, y anymore when you compare it to this y-axis. This y-axis is the slope, really. It's when you put in x, you get the slope out. No longer, when you put in x here, you got a point out. When you put in x here, you get the slope out of this one. And yes, it goes on positive, positive, positive. And same here. This is never going to turn back negative, looking at my original parent. And same for, so this is just going to get more and more positively sloped. And same for this. This shows that the slope increases positively forever. And the same here. This is going to get more and more positively sloped. It's going to get steeper and steeper as it tends down here. So that's the same here. Okay. Now, I haven't even done the question yet. We just talked about the theory. Let's get to the question, which was, do this from first principles. Now, I'm expecting, based off an amateur sketch here, that we'll get a quadratic function. And if I were to solve the quadratic function equal to 0, I would find the 2 points that it would turn, wouldn't I? If I solved it, I would get these 2 turning points. And if I put out any points between those 2 turning points, I'll get a negative slope. And if I put in any points after those 2 turning points, either direction, before, or after, I would get positive slopes. That's what I hope. So let's do it from first principles. So fx is x cubed minus 2x squared plus 3. From first principles. So I need the difference in the y's over the differences in the x. Now, I could put in, and I will put in, why not? The long way. So I'm going to do f of x plus h minus f of x all over x minus x plus h. Oh, sorry, yes. All right. So I'm thinking back to my original thing. If I want to get in general 2 points, get them closer and closer together. If I call one x, the next one's x plus h. So x plus h, take away x on that cubic function. Okay. And what I'm going to do is I'm going to say, well, these points are getting so close together, no matter where they are, they're going to get so close together that their limit, I'm going to say, is pretty much, that they're pretty much zero, but they're not zero. That's what I'm going to say. Okay, so whatever I put in here, x plus h, I get a corresponding y value. When I put in x, I get a corresponding y value. And that's y2 minus y1, x2 minus x1. Now, of course, you have already shortened that down. You don't bother putting in the x plus h minus x, because you know that's just over h, because x, take away x, it just gives h, which is the distance between these two. Sweet, I won't put it here, I'll put it right underneath. So, limit as h approaches 0, f of x plus h minus f of x, the difference in the y's, over the difference in the x, which we've simplified down to h. Now, we've got to apply that to the function that we have in particular. Okay. So, f of x plus h. So, everywhere there's an x, I put in x plus h. X plus h cubed minus 2 times x plus h squared plus 3 all over h. Still, limit as h approaches the 0 has not been applied yet. I haven't brought these two close together. I'm just talking about it in general. X plus h cubed. Anyone know what that would be? So let's link in, right?
X to the third plus 3x squared h plus 3h squared x plus h to the third.
Okay, tell me how you knew that.
Just using Pascal's triangle.
Yes, so this is a binomial, yeah. So see the way binomials are coming into, if this was to the 4, it'd be difficult. But we know something about that row of a binomial. It'll have 4 terms. It'd be 1, 3, 3, 1. So you can go x cubed. Now, even if you don't know that, you can just multiply it out normally. Plus 3 times, well, the x goes down 1 power, and the h comes up 1 power. Plus the x goes down 1 power, and the h comes up 1 power. Plus h comes up a power, and x goes down to 0, and we're left with that. Okay, now you could apply, of course, this here, because the line above this, I think, is 1, 2, 1. Isn't it? And then 1, 1. And then 1. But of course, we know this one, but be careful of this sign. That's a minus 2. So I'll come back to the minus 2. But once again, x squared plus, well, there's 2 x h. So x goes down 1 power, h comes up 1 power, h squared. Okay, plus 3. Now, you could just do that out long way if you're not sure of doing it binomial theorem style or Pascal's triangle style. But that's just showing you. All right, so I need to double all these. I am taking my time here. Is an understatement on this question. But do stop me if you don't follow anything. So minus 2x squared. I think I get minus 4x h's. And then I get minus 2h squared. And then I get plus 3. That's all divided by h. Oh, geez.
So don't you have to like the limit as h tends to 0 for each?
Oh, yeah, I do, yeah. I forgot. Still, I haven't applied this, so I can't get rid of it. Yeah. All right.
Wait, sir, and you have to subtract just f of x.
Oh, I haven't done that yet. Sorry, yeah, you're right. That was just this cubed.
Yeah.
Oh my goodness. X cubed. I subtract minus 2x squared plus 3. Oh, this is so long. So that's, pretend that's tied onto there. I'm tied onto here. I'll put it tied on here. So minus x cubed. I'll apply that minus plus 2x squared plus minus 3, which is minus 3. Okay. Now what I hope here is that this bit that I've minused, that Rigel reminded me of, otherwise I would have gone wrong. This bit that I'm taking away here at the end, the f of x plus h minus f of x, will actually get rid of the f of x. If you think about it, the same way the x is kind of cancelled here, the function with x in it, should kind of disappear out of this. And we should be just left with kind of the function with the h's bit applied. So let's look at that. X cubed is here, and it's taken away at the end here. Plus 2x squared, does it have a minus 2x squared buddy? It does. And minus 3 has a positive 3 buddy. And what happens is this fx function has actually, well, not disappeared, but it's subtracted this fx function, which kind of makes sense, hopefully. The rest of the terms has a h, 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 h. Okay, they all have h's in it, so the h can be factored out. So let's do that. H times, well, that's 3x squared plus 3x h. That's plus h squared. And factoring minus 4x, well, h is gone from that one, minus 2h, all over h. Limit as h approaches 0 still. Okay, that goes into that once. So I've 1 at the bottom, which is great, which now means I can apply my limit, because no longer will a 0 mess this up. So let's apply the limit. Anything with which h in it will tend to 0. So 3x times h will tend to 0. H squared will tend to 0. This will tend to 0. So what am I left with? 3x squared minus 4x. The limit has been applied. So f dash x from first principles is 3x squared minus 4x. Now, I'm not content with that answer. I'm still thinking about this graph. First of all, it is a positive quadratic, so that's good news. I can factor this, can't I? If I let it equal to 0, I'm going to factorize a little bit so I can solve it. So I don't need to do out the full quadratic formula or anything. I can just do that, can't I? So x is 0, and x is, I think, 4 over 3. Are we happy with that?
Yes.
Okay,
Yeah.
so this, of course, that's the end of the question as you know it, but I'm just going on. That's just derived from first principles. That's done. Okay, so that's telling me that this graph crosses at 0 and positive 4 over 3, so maybe here.
So
Now,
the initial point that we guessed, but like I think it was 1, 2. Wouldn't that be -1 then? Because the slope would be underneath the x-axis.
oh yeah, so as I said at the time, this was an example. Yeah. Yeah. So of course, we can start to look. Hopefully, if I put any point between 0 and 4 over 3, so 1, as you say, Rigel, I would get, well, I'll either get a positive or a negative number. So it'll either be here or here. And that will tell me the shape of the curve a little bit. So if I put in 1 here, 3 times 1 is 3 minus 4. So that gives minus 1 out. So if I put in 1, which is maybe slightly towards this point, I get minus 1. Yeah? If I put in a number more than 4 over 3, so 2, for example, 3 times 2 squared. 2 squared is 4. 3 times 4 is 12. Take away 4 times 2 is 8. So that gives 4. That's definitely positive. And actually, the further I go away, if I put in 10, for example, the x squared is going to take over big time here, isn't it? So if I put in another point, it's going to be way up there and way up. Any point is going to continue on. And if I put in a point that's below 0, so try minus 1, minus 1 squared is 1. 3 times 1 is 3. Minus 4 is 7, isn't it? I think it's 3, 7, minus 4, minus 1, so 7. So even minus 1 gives a positive number now. What have I formed? Well, I've formed
Quadratic.
my quadratic. Now, this is where I said it was. It's slightly over. And possibly I should have recognized that from the form of this. There is no x term. So therefore, maybe you would notice that there would be no, it would cross at 0, 0. But maybe that you haven't noticed that yet. But I should have noticed it. But anyway, I can definitely say that the slopes between 0 and 4/3 are negative. I've tested one of them, the one, and the slopes after that are positive. That means, well, I can draw now using, well, not integration, but I could draw a sketch of my cubic. Tell me about x equals 0. X equals 0 on this graph suggests that the slope at that point was 0. Does that mean
That's the stationary point.
that's a stationary point then? Yeah. Does that mean that's the point there, 0, 0?
Not necessarily, no.
No, not necessarily. Actually, you can probably tell me what the point is from the graph function. What's that point when x is 0?
3.
3.
3, yeah. So actually, in this one, there. And when x is 4/3, somewhere here, there's another stationary point. So where would I put that? So is it? Do you think it's above or below the x-axis?
Would it be below, because based on the quadratic you drew on the left side, the second stationary point would be negative?
And that's mixing up gradients with points. These are the gradients.
Oh,
So
right. Yeah,
what
yeah,
that says, so far we've worked out that after 0, gradient's minus. So it's going downhill here. Before 0, it's going up to that point. They're all positive slopes. Boom, 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 boom. All the slopes of the tangents are positives here. The point here is actually a negative point, isn't it? When we sub in x, we actually get a negative y value. The slope, though, is positive. The change is positive. Okay. So I know that at the second place, x 4/3, it stops. It turns again. It's another stationary point. The slope is flat of the tangent. Is that point above or below the x-axis is the question. Well, I could know for sure if I put it into my original function, couldn't I?
Yeah.
Oh, 4/3 cubed. Let's put it in. 4/3 cubed, it's going to be 64/27 minus 2 times 4/3, which is 32/9, plus 3. Oh, okay, so that's going to be about 96/27, I think. 96/27.
Wait, so you didn't multiply it by...
Oh, did I not multiply by 2? I did,
No.
didn't I?
did you square it?
16/9, yeah, it's 4/3. 16/9, and then I multiplied it by 2. I could do it on a calculator, of course, but 64/27 minus 96/27 plus 3. So what's 64/27? Take away 96/27. That'll give minus 32/27. And minus 3, that's going to be positive. Plus 3 is going to take over there. So it's just positive. So it's not quite going to dip below. It's about here. It's not dipping below before it turns off again. Positive, 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 minus, minus, minus. Now the minuses here, remember, are referring to the slope of the tangents at those points. Here and here, the slopes are 0. They're the turning points. We've just found the turning points. Let the gradient function equal 0 to find the turning points, which will, I don't know if you've done that yet. And then it goes off. The slopes increase forever after that. Now, these minuses and pluses, once again, do not be confused with y values. For instance, if I sub in x is equal to 1, I'll probably get a positive y value out. But the slope is negative. And that's what this graph is showing. The slopes are on the y-axis. This one, the points, y, are on the y-axis. This is the slopes. So it's important that you get that relationship between these two graphs and understand what each value means. The difference between, as we did at the start here, subbing in 1 into the function, you got 2 out. That was a point, 1, 2. But when we subbed in 1, we actually got, what did we get, -1 out? And that's the slope of the tangent at the same point. So it's a different sign, and that makes sense if we look at our graph. The slope at 1 was negative, which is interesting. Okay. Phew. Any particular issues that you've come across, maybe in chapter 16?
There was one question that had to do, I was using with
Sines and cos, trigonometry?
Yeah, the first principle.
It was like example 5, and it just, I mean, I don't know, it's a little confusing.
I'm going to presume that he uses trigonomic double angle formulas and trig identities. Now, Rigel, you would have done those last year, no?
Yeah.
Okay.
But it's probably need some refreshing.
Dustin, did you do many trigonomic identities, compound angle formulas, such as, you know, cos A plus B, what that equals? Even if you don't remember, cos squared A plus cos squared B, or sine squared B equals 1. This kind of stuff. Do you remember doing this last year? Dustin? Dustin's maybe not here. Badai, have you come across these before?
We did a very slight overview about it, but it was we didn't really go in depth with it, so I don't really remember much.
Stuff like sine 2a is equal to 2, sine a cos a, stuff like that. Okay, they're in your formula booklet. They're just applications of trigonometry. They would have been prior knowledge for the course, so I'm not sure Dustin knows them. Okay, so you're looking at example 5. Let me find that. Okay, yeah, so that's just manipulation of trigonometry, yeah, which would be, we're not going to heavily focus on that yet because we're going to go back and do trigonometry soon. So if there's something like that, you know, you can delve into it and try it if you want, but I'm not that interested in those trigonometry proofs type of ones where you have to manipulate all these, it's manipulation of these formulas.
All right.
I'm more interested in, so for instance, yeah, like this show that in, I don't know if you're looking at chapter 16 now, the review said 16b, like the second last question is more of that trigonomic manipulation. Show that sine a plus b minus sine a minus b is equal to 2 cos a sine b. We'll be doing that when we hit trigonometry. I'm far more interested that you understand what these graphs mean just using more algebraic functions than trigonomic functions.
Yeah, all right.
So, in general, you should be pretty ready for chapter 17 now, based on what we did there. And chapter 17 talks about the rules, the simple jump. Have you looked at the rules yet?
No, not yet.
Differentiation by rule. Let's look at differentiation by rule. Now, differentiation by rule is just a fast first principles.
Yeah, isn't it like NA to the power of n minus 1 for like the derivatives?
It's nx to the
Yeah,
n
nx,
one.
n minus 1.
Okay,
Yeah.
so we're going to look at the function, and we're going to look at its derivative, and yeah, we'll come up with that. So I'll tell you what the derivative here is 3x squared. Now if we have x squared plus 2x plus 3, the derivative of that is 2x squared plus 2. If we have the derivative of x to the 4 plus, let's go 2x to the 4 plus 3x squared minus 1, the derivative of that is 8x cubed plus 6x. Now, I did that without even...
Oh yeah, sorry, I did this last year a little bit.
Yeah. So what happens is, from first principles happens here. First principles happens in this arrow. But of course, if we notice, first principles was long, but we will notice that the derivative of this is 3x squared minus 4x. That was its derivative. We found it down here. We can get there straight away. Multiply down by the old power and subtract 1 from the power. So multiply down by 3 and subtract 1 from the 3 as if you've used up one of them. As if. Multiply down by the old power here. 2 times 2 gives 4 and subtract 1 gives...
Constants are always equal to 0, yeah?
Yeah, so constants will equal 0. Yeah. As in they don't really affect the slope.
What about, I remember doing a bit of x to the power of negatives.
Yeah.
So there's no way of really knowing or going backwards from a derivative or a differentiation or derivative because you don't know if there's a constant or not.
Mm-hmm. So there is a way of going backwards, but what happens is you don't have the constant. So what you need to put in, if you're going backwards, is a c, a constant.
Yeah, okay, I do remember.
Yeah. So that's integration. So if we were going, we could get from there to there, but no, it wouldn't be plus c there. We would get 2x to the 4 plus 3x squared, but we don't know the constant. We need an additional piece of information to find the constant. So often when you do integration, which is going this way, they will give you an additional bit of information. For instance, the point 1, 2 lies on this original graph. As soon as I know that, I can put in 1 and then find out what c is, because that will all equal 2. So that's an example of an integration style question, which is a bit down the line. Because differentiation by rule, yes, the standard differentiation by rule is multiply down by the old power and then decrease the power by 1. So multiply down by 3 and then decrease by 1. And that's by rule, which is, of course, the short way of doing first principles. Now, this can get difficult. As Badai says, you could be... this, of course, f dash s is still the gradient function, but we're just getting there a lot quicker. So if we're left with something like x squared minus x, I'm doing another squared, plus 2 all over the cube root of x. And that's its original function. And I want to find the function of the gradients. What's the function of the gradients going to look like? Do I panic?
No, just start with the numerator, and I mean, the denominator, I think it'll be to the 4th root because you're still taking 1 degree down, right?
This differentiation by rule only works if you have individual terms.
Can you just move that to the top?
So we got to make each of these an individual term. So it's x squared. Now I don't want the cube root. I want x to the power. What's x to the power of?
1/3.
1/3, thank you. Minus x over x to the power of 1/3 plus 2 over x to the power of 1/3. Okay, that's still the function. We can tidy this up. So Rigel, give me what the next line should be if I just tidied that up, subtracting the powers.
X to the negative 2/3. Or
5 over 3.
Yeah, sorry, add them.
So we're subtracting the powers, yeah?
Yeah. X to the negative 2/3, I guess.
Negative 2/3? It's 1 take away a third. It's going to be positive 2/3. Plus 2x to the negative 1/3. We finally got there. Finally got your negative in there.
Yeah.
Okay, now multiply down by the whole power. 5/3. X. Subtract 1 from this. So subtracting 3/3 will give me 2/3. That's to the power of 2/3. I should write that better. Let's just write that again. 5/3 x to the power of 2/3. So I've subtracted 3/3 from that first one. Multiply down by the whole power. So that's going to be minus 2/3 x. Subtract 1 from this will give minus 1/3. So minus 3/3 again. And then multiply down by the whole power. Minus, well, that's going to be minus 2/3 now, because 1/3 times 2 is 2/3, of course. X, subtract 1, that gives minus 4/3. Now, if I put a value into this, I will get, this is my gradient function. If I put a value into this, I'll find the slope of this original one at any point along it. If I put a value into this, the original, I'll just get a point on the original graph. If I put a value into this, I'll get the slope at that point. So is it going up or down, and how steep it is? Now this looks like a nightmare. If you're thinking about this as a graph, what that graph would even look like, you could put it into Desmos, have a little look. Do these two compare? They will compare. You'll see the turns match the slopes, and might be interesting to have a look at. Maybe you can look at that one yourself. That was from page 439, question 3P. I just took it out of the book there. Okay. Now, there's further rules. Now, I don't think we're going to get to these rules today, and I don't want to overly confuse the issue. Tomorrow or Thursday, when we're in school, we'll go through all the rules to get fast from first principles. But of course, you can see how first principles, although is straightforward, it can be long, can't it? Even our simple example, this is a relatively simple example with just a cubic equation, it ran over the length of my page. That was probably because I forgot it, but I forgot to subtract. But you can only imagine how messy first principles would get if you're dealing with this kind of deal. So that's why we need that short method. We no longer care about the distance between the thing and the thing anymore, h getting smaller and smaller, if we can just jump to our answer by a simple rule. And they're going to get more and more complicated. For instance, what happens when when you can't do this? What happens when you've got something like 3x squared minus 4x plus 3 over x squared minus 2 to be squared? Sorry, I'm off camera. What happens if we want to find this is a legitimate function? We're dealing with similar ones in the last unit. Legitimate, it will have slopes and stuff at different points. But if I just do this by rule, it wouldn't work, because each term would have to be divided by this, and then my rule won't work anymore because I can't get a constant power, because it's going to have x to the 4 and x squared on the denominator. So we need a rule for that. We also need a rule for if it's, what happens if I have this? Because this in itself contains x cubed, x squared, and x, because this would be cubed out. Or what happens if it's to the power of 5? There's a rule for that as well. There's rules for all different ones, and there's also rules for integration, which are even harder to go backwards. But we'll look at all the rules. They call it quotient rule, product rule, chain rule. We'll look at those 3 rules on Thursday. So if you want to work ahead to that, that's all in chapter 17, and we'll go through those on Thursday. So we'll try and get through chapter 17 on Thursday, including exponential functions, logarithmic, trigonometric functions. We'll try and include those. So I don't think we won't get to implicit on Thursday. That might be a step too far. But you can have a look at it. We won't get chapter 17 finished by any stage this week, and not next week either. Because implicit starts to get difficult, and so does the trigonometric and logarithmic and stuff like that. So my goal is to finish chapter 17 perhaps by the first week back after winter break. Because once we have all the rules for differentiation, we can apply them to anything. We can get gradient functions for anything we want. And we can get the gradient of a gradient function for anything we want. Well, not anything. There's no complex ones at the moment. We won't go there. And that's chapter 18 then talks about the application a little bit more. And then chapter 19 definitely talks about it with the kinematics, rates of change and stuff like that. And then we'll be finished. But we need, then we finish differentiation. We need to move into working backwards, integration then. So that's why this is such a long unit. We need to build up a lot of skills, but we're going to break it down into just chapter 16. You guys make sure you know chapter 16 inside out by Thursday. I'll give you some questions you have to do for homework, not many, and then if there's any problems we can run through at the start, and then we'll start on question 17, or chapter 17. I do recommend that you work forward in chapter 17 and have a look at these rules before I get to them, and hopefully it'll be a lot quicker than on Thursday. So to sum up, in about 5 minutes I will send you your homework, which will be maybe 3 or 4 questions, not too many, on chapter 16, and then you can work ahead yourself in chapter 17 and do whatever you want. Any problems, questions, queries?
This differentiability and continuity, is that